AP Chem Scholars, it's me again, and we're here for section 3.11, Spectroscopy and the Electromagnetic Spectrum. Okay, when we talk about spectroscopy, we're talking about the spectrum, right? We're talking about studying it, breaking it down, and looking at colors for the most part. Yes, it goes beyond colors. We could talk about the whole electromagnetic spectrum and go into visible light and also infrared and ultraviolet and beyond. And we are going to talk about that a little bit more in one of the next sections. So let's jump into it. So when we talk about spectroscopy, okay, we're talking about somehow viewing the spectra of things that are produced. We looked at spectroscopy when we did flame tests, and if we did any of the emission spectra lines. I know we did something more or less on the computer related to that. I don't know that we did it in the lab in the last year or so with you guys. But the point is, we've done some investigations with this idea. When we talk about the electromagnetic spectrum, again, we've gone through the idea of waves and having wavelength and frequency, and the fact that visible light is just one little part of the whole spectrum. We know that there's these things called wavelength and frequency, and wavelength and frequency are inversely related. So as the wavelength gets bigger, that means the frequencies get smaller, and we see that represented there. We have talked about the ideas of speed equals wavelength times frequency, and energy equals Planck's constant times frequency. So we're going to be circling back to those a little bit more as we talk about this. So what we're looking at, though, is also how it's generated. And we talked a little bit about the idea of what a flame test is and how it happens and so on. So when we irradiate a substance, give it energy, I should say, okay, we take a sample and put it in a flame, or we take a gas like a neon tube and shoot electricity through it. Okay, we cause the electrons to enter into an excited state. So we're getting transitions between electrons. And as the electrons are jumping back and forth, okay, as energy is absorbed, it's got to come back out eventually. And depending on how much of a jump there's different amounts of wavelengths, okay, because every energy level has its own amount of energy, and any change then was going to be related to a frequency, which means it's related to a wavelength. Okay, so because of this, most of the generation in this type, when we talk about electrons jumping back and forth, is visible light, like these colors that we would see, but it also would be some ultraviolet light. There may be a tinge of infrared, but we're going to stick mostly with the idea that whenever we're talking about electrons jumping between energy levels, we're going to have visible light and ultraviolet light generated. Now, if we want microwave energy, we have to help these molecules rotate. When we add energy, obviously, on an atomic scale, we said that gets the electrons excited, but adding energy to molecules actually can cause them to move faster, and so one type of motion is rotation. Well, it turns out that as they try to release that extra energy, or I shouldn't say they try, as they end up releasing that extra energy as they go from a faster motion to a slower motion, they'll release a photon that's going to be in the microwave region. Okay, so we talked about visible light and ultraviolet for the electron transitions. For molecular rotations, we're going to talk about microwave. And then we have one more type we have to talk about, and that is vibrational motion. When they are vibrating, because of this added energy, as they start to, as they lose that extra energy, again, a photon is going to be emitted, same idea that we're talking about, but now it's definitely going to be in the infrared region. So we have three different things going on: electron transitions, molecular rotations, molecular vibrations, and we had different types of radiation. And that is one of the things the AP loves, is to hit you with graphs and pictures and talk about the fact that rotation gives off the microwaves and vibration gives off infrared and the jumps. Now, visible light, it's real close. It's a small section. The difference has to do with where the jumps are. Okay, you see how it says outer shell versus inner shell. The closer to the nucleus you get, the more energy you're going to be releasing. And so that's where it starts moving past visible light into the heavy ultraviolet range and possibly even into the X-ray range. But you don't have to worry about X-ray. We're just going to talk again about it being visible and ultraviolet for our purposes. Okay, so let's look at this question and see if we can rationalize it. So there are two peaks on this graph, and we wanted to explain them in terms of the type of electromagnetic radiation and the probable cause for that. Okay, so let's backtrack a few slides here just to emphasize a point before I do that. It's hard to see those numbers here, but numbers that you are supposed to reasonably know is that visible light runs from roughly 400 nanometers to 700 nanometers. Actually, this is 400 nanometers, this is 700 nanometers. They're showing it in frequency. I got the wrong graph there. Oops. So you got to keep in mind those numbers. Visible light is 400 to 700. So as I look at this wavelength, I see that the first peak is at 600. So I can pretty much say that this is going to be visible light. All right? No doubt about it, visible light. Now we're going to go to a higher wavelength and go to the next peak. Okay? So the next peak is going to have an even higher wavelength. Well, if we're going higher wavelength, okay, that means that we're going to lower frequencies. All right, so let's go back to that graph one more time there. Okay, so wavelength is increasing on this graph this way. Is that right? No, energy increases. Wavelength is increasing to the right. Okay, yes, sound waves, etc. So we're in visible light. If we're moving towards longer wavelengths, we've got to be moving towards infrared. All right, so that tells us clearly that the second peak is in infrared area. And if it's in the infrared area, we said that that's got to be due to molecular vibrations. So we know that we have electron transitions creating visible light, and we have molecular vibrations creating infrared light. And there's that rationale that we just talked about. All right, another short topic for you. You got to love these. All right. Short practice also on the AP. Have a good one.